Welcome back for the last video of Chapter 2, Lesson 2.8. This is going to be all about linear functions and models and variation. So earlier in Chapter 2, we kind of did some remembering and refreshing on linear equations. And a linear function, reminder, can be written in two ways. It can be written in the slope-intercept form of the function equaled mx plus b, where m is the slope and b is the y-intercept. Or it could also be written in like a point slope form using 2 points, x1 and y1. A linear model is a different type of linear function. It's a way that we're going to model real life data when it doesn't work out perfectly. So real life things don't always fit a model or a function in a particular perfectly way. And so we have to have a way to say, I think it kind of looks linear, and this is the model that best fits it. So we're going to learn how to do that today. So example 1 says, if 32 degrees Fahrenheit corresponds to 0 degrees Celsius, and 200 degrees Fahrenheit corresponds to 100 degrees Celsius, find a linear function that converts the Fahrenheit to Celsius temperature. So I'm going to let x and y be Fahrenheit and Celsius. So the first thing I need to do is get my slope. And my two points are going to be 32, 0 and 212, 100. So my slope is going to be 100 minus 0 over 212 minus 320. So that's going to be 100 over 108. And I'm going to go to Desmos to figure out what that is because I don't know. And that is 0.926. Okay, then I'm going to find out what my y-intercept is. So I'm going to use my point slope form, which says y minus, and mine is, I'm going to use 32 and 0, so y is 0, equals my slope of 0.926 times x minus my x. I'm using the 0.32 and 0, so my x is 32. Here's my paper. So this is what I have for it so far. Y minus 0, which is my y1, equals my slope times x minus x1, which is 32. So y equals, because y minus 0 is y, and then I'm going to distribute here. So this is going to be 0.926x minus, and then 0.926 times 32. So 0.926 minus, I'm going to find out what that is in Desmos. And it's 29.63. So this equation allows us to take any Fahrenheit temperature and put that in for X, and it will tell us what the Celsius temperature is. Now that model worked out perfectly because we only had 2 coordinate points. And so if you have 2 coordinate points, your slope goes for sure through those 2 points. And so your line goes for sure through those 2 points. However, if you have multiple data points that you're trying to find a model for, you have to do it in a little bit different fashion. So we're going to create in Desmos what is called a line of best fit. So the first thing you're going to do is click the plus button on the top left of your screen and choose a table. And then enter your data into X1 for your independent variable and Y1 for your dependent variable. Click on the magnifying glass at the lower left so that the graph will show up and it will scale itself. Then in a new line, type y1 tilde, not an equal sign, but a tilde, and then mx1 plus b. It is going to give you your line of best fit. It will tell you the slope that best fits your line and the intercept that best fits your line. It's also going to give you something down below called r squared, and that is what we call the coefficient of determination. And that coefficient of determination tells you how well your data is fitted by that model. And we would really like that to be bigger than 0.8. Okay, so let's go check out our example here. So we have an example here that says the following table lists the population of those in the US who are 65 years of age or older in millions. Our data that they gave us is in years. So when we're given data in years, which are very large and would be very large for scaling on the graph, we usually use a year since date. Now, they told us down here, not till part B, to use the number of years since 1995 as the independent variable. So that means since 1995, my year is going to be 0 because that's my base year. And then 2000 is 2000 minus 1995, or 5 years after my base year. 2005 is 2005 minus 1995, or 10 years after my base year. And 2010 is 15 years after my base year. So I'm going to put these years since 1965 in for X1, and then my population in millions in Y1. And we have to remember that it's in millions. So this would be 31.7 million people who are 65 years of age or older. So A says, what general trend do you notice in these figures? It appears that the population of people that are 65 years or older is growing. That population of people is growing. Fit a linear model to write the function for this set of points using the number of years since 1995 as the independent variable. So we're going to type in Desmos. You're going to want to write this down. Y1 tilde. This is to the left of your 1 key on your keyboard. And then you're going to type mx1 plus b. A few things to note. We do not use an equal sign, and we also have to reference the column that our data is in, y1 and x1. Now, if you have multiple data sets in, for some reason you're working with different data sets, make sure you know which one you're using. We're going to be using M1 and X1. So let's go ahead to our Desmos. And here we are. So you're going to press this plus button right here that says add item, and you're going to say table. Now mine says X2, Y2 because I've already put our data in up here. So I'm going to use the one that says X1, Y1. And I entered my 0, 5, 10, and 15 for the years since 1995. And then I also added in my Y1, my number of people in the population that are 65 years or older. Now, you can drag these around these rows. So I'm going to drag this up here. So I want to take Y1 and I'm going to use tilde and Y1 and tilde, and I'm going to model that as mx1 plus b. So my m is 0.466. That is the slope, and b is 31.03. That's my y-intercept. My coefficient of determination, my r squared, is 0.9442, which is really good. But I forgot to look at the graph of the data. So let's go up into our table. The bottom left of our table, there is a magnifying glass. Go ahead, see where my mouse is. It says zoom fit. Let's click on that. It graphed our data for us. Now I'm just gonna scale out with my rolling mouse here. Now the red line is the line of best fit. And you can see that it doesn't go through any of my 4 numbers, but it is the best equation for a line that fits my data. So let's go ahead and write this on our letter B. We're going to call it y equals, and then my slope is 0.466x plus my y-intercept of 31.03. Okay, now it says use your function to predict the number of people over 65 in the year 2013. So 2013 is going to minus 1995 is going to be X equal to 18, because 18 years after 1995 is 2013. And so we are going to go ahead and go search for that on the internet. We're going to search for that value here. In 2013. Let's see if they actually have the data. So there is a table from the census.gov. It looks like it's giving us that data for 2013. So this is great. This is population by age. Let's check this one out here. So it looks like, let's use both sexes, and it says under 62. Okay. There's a total of 311, and this must be in millions. Numbers in thousands. Okay. So 311,116. Let's just write that down. 311,116, and then 3 more zeros because it says it's in thousands. So 311 million, but we have to subtract away everybody under 65. So that would be everybody under 65. So it would be this 229. I'm going to do it right here. I'm going to take my 311,116, and I'm going to subtract the 229,338, and I'm going to subtract 2,880, the people in the 55 to 59. And then I'm also going to subtract the people that are 60 to 64, 17,611. Oh. Subtracting 17,611. Okay. So it looks like the number is 43287. And that, let's go back to my paper so you can see what I'm writing here. You have to do a little research, and research is good. And that's in thousands, so I have to add 1,000 for 3 zeros for 1,000. So it's really 43,287,000, because our number up here is in the millions, right? So really it's 43.287 million. So the actual number in 2013 was 43.287 million. And let's predict, so this is the actual number. Oops, we did letter D. So the prediction when X is equal to 18 is, let's go to our equation and predict what that is in Desmos. So using my model, I can go to, I can actually go on my graph here and scroll to where I get to 18. And so it looks like 39.418. 39.418. So we predicted 39.418, and the actual is 43.287. So we under predicted a little bit. And that's okay. So get some practice. We're not going to be doing a lot of this modeling this semester in assessments, but it's good to learn how to use modeling because real life, we have data all around us. And so there's definitely classes that you might do some modeling. The last big topic that we're going to look at is called variation. And we deal with variation every day. For instance, the faster you drive to work, the faster your car gets used up in gas. Also, those go up together. So the faster you drive, it goes up, right? Your speed goes up. Your actually the gas in your car goes down, right? The speed goes up, gas in your car goes down. Also, the speed goes up, the time it takes you to get to work goes down, right? The faster you drive, the speed goes up, the more likely you are to get in an accident. So the one where they go up together is called direct variation, and the one where they go opposite of each other is called inverse variation. So an equation where we're using direct variation, you might see it as the function is equal to k times x, or y is equal to k times x, where k is the constant of variation. And that might be like your miles per hour. So let's look at an example. It says, let y vary directly as x. So that means we have y equals some k times x. And we want to find k. What is the constant of variation? And we want to find the equation to go with it. So when y is 35, we know that x is 10. So we want to find out what our constant of variation is. So if we divide both sides by 10, we can find out that k is 3.5. So our equation is y equals 3.5x. Example 4. The volume of a gas varies directly with the temperature. Find K if the volume is 50 cc's at 40 degrees Celsius. What is the volume if the temperature is 60 degrees Celsius? So we need to first find our K. So if they vary directly, we know the equation looks like this. And my independent value is the temperature is my independent. So that's my 40. And then my that's my x, and my volume of gas is my y, and so that is 50 cc's. So to find out what my k is, I need to divide by 40. So I get 5/4 is k, or 1.25. So my equation is y equals 1.25 times x. And then they want us to do some predicting. What is the volume of the if the temperature is 60 degrees? So y equals 1.25 times 60 is 75 cc's. So 60 and an extra quarter would be an extra 15. So 75 cc's. Now, inverse variation works just the opposite. So when a model gives rise to a linear function of the form y equals k over x, or you might do x times y equals k, is again the variation constant or the constant of proportionality is k. So this is inverse variation. So this says, that's not number 13. Let y vary inversely as x, and y equals 1/5 when x is 3. Find k. So y, we know that x times y equals k. And 1/5 times 3 equals k. So k must be 3/5. Okay, so my equation is y equals 3/5 divided by x, or 3 over 5x. It says, what is y when x equals 5? So y equals 3 over 5 times 5, or 3 over 25. Try this in an example. It says the time t required to drive a fixed distance varies inversely as the speed of the car. So the time t varies inversely as the speed. Okay, it varies. K is always on top of the independent variable. If it takes 2 hours to drive to New York, from New York to Philadelphia at a speed of 55 miles per hour, how long will it take to drive the same route at a speed of 50 miles per hour if you need to slow down? So we know that t equals 2 when s is 55. So I can multiply both sides by 55 to find out that k is 110. So my formula is t equals 110 over s. So now I know if I'm only going 50 miles an hour, my time is going to be a little more. I'm going to find that out in Desmos here. $110 divided by 50, and that's 2.2 hours. So instead of 2 hours, it's going to take 2.2 hours to get there. So that is the end of our lesson for 2.8. Catch me back for more videos. Make sure to work on the review before you take the test. Have a blessed day.